Okay, all right. So you move the thing, yes. Okay, sorry, Tom wasn't here. Tom is on furlough, and so we didn't have any experts setting this up. I'm trying to put the next homework assignment on the, thank you, on the web, thanks, shortly. In other words, tonight, tomorrow, something like that. So let's see, we've been talking about Fourier transforms. One thing that I forgot to mention was what happens if you integrate a Fourier transform. So let me just point that out. By the way, thanks for erasing the board. So let me just move it here. And so suppose f of x is the Fourier transform minus infinity plus infinity e to the I kx f hat of k dk over square root of 2 pi. Okay, so this is actually the inverse Fourier transform, but for some reason, I don't know, I always feel better when it looks like this. Okay, so what if you integrate? Integral, and this is the indefinite integral. If you do the definite integral things, the notation gets very complicated. If you integrate indefinitely, you get minus infinity plus infinity, simply e to the I kx over ik, f hat of k, dk over root 2 pi. And I'm going to use the notation prime f of x for the indefinite integral. Does anybody know a better or some other standard notations for indefinite integral, first, second, third indefinite integral? All right, well, we can go with this. In particular, then, the nth indefinite integral of f of x is then just minus infinity plus infinity e to the I kx over I k to the n f hat of k dk over root 2 pi. So one of the lovely things about Fourier transforms is it's very easy to integrate and differentiate. Remember that if you differentiate the nth derivative here of f of x is the integral minus infinity plus infinity I k to the n e to the I kx f hat of k dk over root 2 pi. So these things are very easy to integrate and differentiate. All right, we were talking last time about momentum and momentum space, and in particular, it's gotten to the point of the Fourier of the uncertainty principle. And in order to make things simple and make use of the Fourier transform of Gaussian, which we did in an earlier section, I took as the initial wave function psi of x, which we can write this way as x psi, as some sort of a Gaussian, e to the minus x over a squared. And the first thing we want to do is we want to normalize this to unity, so that 1 is the integral minus infinity plus infinity psi of x squared dx, and that means we have n squared integral minus infinity plus infinity e to the minus 2 x over a squared dx. Okay, well, when you do that, you find out what n is, and in fact, psi of x you then get as 2 over pi to the 1/4 e to the minus 2 x over a squared divided by the square root of a. So that's our normalized wave function. Now, as we may have already said in this course, and as you probably already know, the mean value of an operator A in a state psi is just the diagonal matrix element of the operator A in that state psi. More generally, if this is a system described by a density operator rho, then the mean value of A is the trace of the density operator times the operator A. As usual, when I put physics into this math methods course, it's so that you learn the physics, well, you know you're not going to be tested on it, because you're not going to be tested on math. I don't want Finley to hear that, but the hope is that you learn some of the physics just as you're learning the math. And by all means, ask questions about the physics as well as the math if you want to. Okay, so in particular, the mean value of the operator x then will be psi x psi, this is the state psi, and that is just going to be then the integral of x psi squared dx from minus infinity to plus infinity. And this, in fact, is 0. Why is it 0? It's 0 because this is an even function, this is an odd function, and this is an even interval, or symmetric interval, let us say. Symmetric about x equals 0. So for those three reasons, the thing is 0. You don't have to actually do the interval. Okay, now another definition, dispersion. The dispersion of an operator A, or the square of the dispersion of the operator A, is the mean value of the square of the difference in the state psi. So that's the square of the dispersion, where A, of course, is the mean value of the operator A. In particular, if you're more generally I shouldn't say in particular, I should say more generally, it's the trace of A minus, the trace of rho times A minus, and this mean value of A, of course, is itself the trace of rho A. So that's the expression more generally for the square of the dispersion of operator A, the system described by a density operator rho. Density operators, remember, are Hermitian, non-negative unit trace. Apart from that, there is no restriction. So in particular then, the value of the dispersion position for a particle in the state psi described by this Gaussian wave function is then the mean value of x minus the mean value of x squared in the state x. And now this is a little bit simpler because when you multiply that out, you get x squared minus 2x mean value of x plus mean value of x squared times psi. And, well, let me say, in fact, I should have done this more generally. Let's expand this thing. If we expand this thing, what we get is psi a squared minus 2a times mean value of a plus mean value of a squared psi. This and that are numbers, so this is effectively mean value of a. So it's minus twice the mean value of a squared plus the mean value of a squared. So it's actually psi a squared minus a squared psi. Or effectively, it's psi a squared psi minus mean value of a squared. Because psi is normalized to 1. So in this particular case, when the mean value, since the mean value of x is 0, this term vanishes, that term vanishes, and delta x squared is just the mean value of x squared in the space time. All right. And so that's just the integral minus infinity to plus infinity x squared psi of x squared dx, and that turns out to be a squared over 4 when you take into account that psi of x is this expression here. Any questions? Okay. Now, to find the dispersion in momentum space, though, we need to find the momentum space wave function. And in the last section, we saw that that was the Fourier transform of the position space wave function. So psi of p, and what I'm doing here is I'm basically using what latex calls var phi, but I think of it as just an easy way of writing psi. Anyway, so I'm going to call it psi of p psi, and this is the integral minus infinity plus infinity, p x psi, or to write that a little more clearly, those of you who so this integral minus infinity to plus infinity of this outer product, dx, is just the identity operator. And we've seen that p of x is equal to e to the minus I px over h bar divided by the square root of 2 pi h bar. And so what we have here then is that psi of p is integral minus infinity plus infinity. This black is just too strong at this point. We have then, all right, so this is then e to the minus I px over h bar divided by the square root of 2 pi h bar, and the rest of that is x psi, or equivalently psi of x. And so substituting in this expression for psi of x, what we get is that psi of p is then integral minus infinity plus infinity dx over root 2 pi h bar. Sorry about that, funny looking h bar. E to the minus I px over h bar 2 over pi to the 1/4 e to the minus x over a squared divided by the square root of a. And that's just the Fourier transform of a Gaussian. You do it by completing the square, and we've done that a couple of times. And then the answer is square root of a over 2h bar. And equivalently, an internal square root of 2 over pi e to the minus ap squared over 2h bar squared. So that's our wave function in the position space. It's a Gaussian, and remember, if A is big, then then psi of x is way spread out. But then, if A is big and psi of x is spread out, psi of p is very sharply peaked at the origin, and vice versa. That's always the case. The Fourier transforms of a function and its Fourier transform, they have different properties. If one is big at the origin and small at infinity, the other one's small at the origin and big at infinity, and so forth, vice versa. complementary. So the mean value of p is certainly 0 because, once again, this is an even function. P is an odd function. So delta p squared then is simply psi of p squared. It's the same thing as p squared in the state psi. And this is the integral minus infinity to plus infinity p squared p psi squared dp. And so we find that the square of the dispersion in momentum is square root of 2 over pi integral minus infinity plus infinity p squared a over 2h bar e to the minus ap squared over 2h bar squared. I think that's everything tp, and then one finally gets h bar squared over a squared. So notice once again, when A is big, the uncertainty in position is big, but then the uncertainty in momentum is small. And conversely, if A is small, the uncertainty in momentum is big, and then, but on the other hand, the uncertainty in position is small. And what this gives us then is that delta x squared, delta p squared, in this case is equal to h bar squared over 4, and that's an example of the Heisenberg uncertainty principle, delta x, delta p greater than or equal to h bar over 4. In this, sorry, h bar over 2, so in other words, this says this is equal to h bar over 2. The Heisenberg uncertainty principle says this is greater than or equal to. In this case, we saturate the lower bound. That is to say, Gaussians are minimum uncertainty states. And in particular, the coherent state is also a minimum uncertainty state. It's a Gaussian also. All right. Any questions? So this is an example of the uncertainty principle. So just one more. And suppose the state psi of 0, which is right as psi dp, just inserting the identity operator there, and then we have the minus infinity plus infinity dp dp. We then, if the particle is free, then the Hamiltonian is very simple, and the evolution of the state is implemented by this unitary operator, either minus the Hamiltonian, minus I times the Hamiltonian times time over h bar, acting on psi of 0. So this is, in other words, psi of t, and this then is equal to minus infinity plus infinity e to the minus I. Now the Hamiltonian for a free particle non-relativistic mass m is just p squared over 2m. So this is e to the minus I p squared over 2m t over h bar. And what's left is then p psi dp. So this is this evolution in time is this form, and this isn't quite a Fourier transform because the variable p was squared here. but that's the way it is. All right, any questions about that before we go to Fourier transforms and several variables?
When you say Gaussian, can there be anything said about the Gaussian like optical beam? Is it the relationship the same, or is it a Gaussian profile in 2 dimensions?
Well, it's convenient as an example to say that the profile of a beam, say from a laser, has a Gaussian profile, because then you can manipulate it easily. But whether that's an accurate description of the intensity profile of the light coming out of the laser, I don't know. You have to ask Jean-Claude Diels or one of the other laser experimenters.
I think for fiber, that's a pretty good product.
Pretty good.
I work with fiber lasers, so we use Gaussian like optics to do a lot.
I mean, it may be fine.
It's like elliptically Gaussian.
Huh?
It's like elliptically Gaussian.
Yeah, elliptically, I didn't mean it should be circular. How accurate is this? I don't know. Ask one of the guys who knows. I do know, though, that Gaussians are used whenever you can get away with a Gaussian. People like to use Gaussians, and in fact, it's a little bit amusing that in quantum chemistry, people are always using Gaussian wave functions, even though the wave functions of atoms and molecules are certainly not Gaussian, but program runs fast, and so that's what they do. And in fact, some of these commercial programs like Charm also use the Leonard-Jones 612 potential, which is something that Leonard-Jones introduced in order to introduce as a classroom example. He didn't intend it to be used in serious computations in commercial programs like Charm. I like to think about Charm.
How did it get out of this classroom?
Well, like the Gaussian, it's easy to play with. It's 1 over x to the 1 over r to the 12, constant over r to the 12 minus another constant over r to the 6. The 1 over r to the 6 part is not too bad because that's the van der Waals term. But the 1 over r to the 12 is just something you pull out of his nose.
It also, I mean, it does decent under some.
Yeah, as a classroom example, it's good. Yeah. All right. Well, enough. Fourier transforms in several variables. Well, it's what you'd expect. Namely, you just the Fourier transform f hat of k1 and k2 is an integral dx1 over root 2 pi, integral dx2 over root 2 pi. All of these are going from minus infinity to plus infinity. E to the minus I, k1 x1, minus I, k2 x2, f of x1, x2. And the inverse Fourier transform, well, it's integral minus infinity to plus infinity dx1 prime dx2 prime of this integral minus infinity to plus infinity dk1 dk2. And now, since there are 2 of these, you might as well just have a 2 pi, so you have 2 pi here, 2 pi there. And then e to the I, k1 x1 minus x1 prime plus I, k2 x2 minus x2 prime, f of x1 prime, x2 prime. Okay. So in other words, I'm I multiplied, in other words, this thing with the e to the minus I, in other words, this thing is the same, maybe I should have used another step. This is integral dx1 prime dx2 prime over 2 pi e to the I k1 x1 plus I k2 x2 of f hat of k1 k2. So this is equal to that. And then what happens? Well, in here you see that the dk1, dk2 gives you two direct delta functions. Each of them even has the right normalization, 2 pi. And so this gives you integral dx1 prime, dx2 prime, both of them from, say, minus infinity to plus infinity, delta of x1 minus x1 prime, delta of x2 minus x2 prime, f of x1 prime, x2 prime, and that just gives you the f of x1, x2. So in other words, f of x1, the inverse Fourier transform for two variables, f of x1 and x2 equals integral dx1. Wait a second. Now this is integral dk1, dk2. Yeah, leave it dk1, dk2, no primes. dk1, dk2, e to the I k1 x1, e to the I k2 x2, have had a k1, k2, which in turn is using this formula for f hat of k1, k2, but using primes on the x's gives you the rest of this thing. All right? Okay. So in other words, the inverse Fourier transform relation is f of x1, x2 equals integral dk1, dk2, and then just one factor of 2 pi, e to the I, k1, x1 plus k2, x2, and half k1, k2. And in n dimensions, it's just f hat of k1 dot 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 kn is integral minus infinity plus infinity dot 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 minus infinity plus infinity dx1 dot 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 dxn 2 pi, whoops, 2 pi to the n over 2 e to the minus I k1 x1 plus kn xn f of x1 dot 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 xn, and then the inverse Fourier transform is f of x1 dot 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 xn equals integral minus infinity plus infinity minus infinity plus infinity dk1 dkn over pi n over 2, and then just the opposite face with EVI k1 x1 kn xn f hat k1 k. Now, often one writes dx1 through dxn as dnx and dk1 through dkn as dnk. Okay. Whoops, sorry. Okay, any questions? That guy went to Vegas recently.
No, I was on a balloon.
Did you?
Yeah, I went up Saturday.
Yeah, that's why you got that marvelous tan.
know how marvelous it'll be in a couple of days. Hurts.
Ahead of the rest of it. By the way, sunlight after 4 and before 10 in the morning is good for us. Really, between 10 in the morning and 4 in the afternoon in New Mexico, in fact, several. I know 2 faculty members here in the department who are doing with melanoma. The other thing, they both grew up in Texas. New Mexico's worse. Higher. Okay, example of the Fourier transform, Feynman's propagator. Delta f of x. X here is a 4 vector, and we're in natural units. H bar and c equal to 1. It makes the formulas easy to write, easy to understand. And then, when you want to get out of natural units, if you haven't made any mistakes, you then have an answer. It's in natural units, so you don't quite know, but you do know what the dimensions are supposed to be. So then you sort of sprinkle. You think of salt, you think of C as salt and H bar as pepper, and you just sort of sprinkle them onto the formula until you get the right number of them so that the thing has the dimensions you want. And then it's the right answer. So that's the short course in natural units. This propagator then is an integral exp of I k dot x. So it's a Fourier transform, you see. But now it's over k squared plus m squared minus I epsilon. This is a scalar field, or spinless field, mass m. Scalar fields, spinless fields are the easiest ones to deal with mathematically. One of the embarrassments of quantum field theory is that no one has ever seen an elementary particle that has spin 0. Well, at least an elementary particle. The pion has spin 0. But it's not a stable particle. And we made a quark, an anti-quark. Anyway, scalar field plus m. And now we have the d4th k over 2 pi to the 4th. Notice Feynman chose to put all the 2 pi's on one side. So as usual, in all of these Fourier transform relations, there's no convention as to where to put the 2 pi's. I put them in symmetrically. That's the safest thing to do, but that means you have square roots of 2 pi's on both sides of the equation, so it looks something lovely. Okay, what is k dot x? K dot x is that Minkowski inner product. K is the momentum, x is the position, minus k0, x0, and x0 is c times time. In fact, k0 is E over C, but since I work more in natural units than I work on sort of particles, I work in natural units, and I always have C. Anyway, now one of the things that the Feynman propagator gives us is can be defined in terms of the time-ordered product of 2 quantum fields. Quantum field at x and quantum field at y. So this is a space-time point x, a space-time point y, and this is the Heaviside function x0 minus y0 times phi of x, phi of y, plus the Heaviside function y0 minus x0 times phi of y, phi of x. You see these fields, like most operators, don't commute, and so what you do is you define time-ordered product is defined then as if x0 is later than y0, then the theta function is 1, and so it's 5x, 5y, and this term is 0. On the other hand, if y is larger than x, then this term is 0, this term is 1, and you get 5y, 5x. So it's 5x, 5y, whichever is later comes first. And the formula then is that minus I times this is equal to the mean value vacuum of the time-ordered product of 5x, 5y. And this is for the case in which the Hamiltonian of the this is the vacuum state, and this is the case in which the Hamiltonian for the field is just a sum of h bar k0 a dagger k a of k plus a half. So in other words, it's just this sum of harmonic oscillators. Since I'm summing over k, I've essentially put this in a box with periodic boundary conditions. Okay. So in other words, the time evolution of these fields is governed by this simple Hamiltonian, and so that's when this thing is true. But when one does perturbation theory in quantum field theory, which is almost all one knows how to do, then what you do is you have the field operators evolve according to a Hamiltonian like that one, all interactions, and so this is in the interactions interface. So these are the fields evolving in the interactions. There's another way to think of this. Okay. Anyway, it was just an example of a Fourier transform in 4-dimensional. Any questions? And of course, the input will go over minus infinity, plus infinity. And epsilon, I forgot to mention, epsilon is simply an arbitrarily small real number. And it's just, we'll evaluate that when we do complex variable theories. It's just an example of complex. Any questions?
What about this Z and T term?
Z and T.
Well, you get the phi of x and phi of y after you do the integral. But aren't you're integrating over? I mean,
Yes, marvelous. I shouldn't have. See, I wasn't following my notes. This would be for the case y equals 0. The actual case, if we have x and y, this is dot x minus y. And this is okay. Is that what you meant?
Yeah.
All right. Marvelous. Yeah. In general, when I'm writing like this, you can sort of believe it. When this hand is down and I'm writing on the board, you need to check what I'm writing. It's going to be typos, mistakes, and so forth. Okay. Well, Fourier invented his Fourier transform in order to deal with certain differential equations. Now, we saw how easy it was for us to differentiate the Fourier transform. In particular, let's think of Fourier transforms in n dimensions. And so then we can take the nth derivative with respect to xj of some function f of x1 dot xn. And this will be integral minus infinity plus infinity. I'm just going to write this as dnk over 2 pi to the n over 2, sorry. And this is just ikj to the n, to the m, e to the I dot, well, I don't know. Let me write it explicitly. K1 x1 plus dot 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 kn xn times f hat of k1 kn. So that's what the nth derivative is, nth derivative. And in fact, we can define this thing, a shorthand that's commonly used is partial sub m. This is just the nth partial derivative. Whoops. Yeah, I'm writing this. Yeah, I need a J here, and I need an M here. And I think I should have left the subscripts down there actually, rather than the superscript. Okay. So this is so simple then that we can go beyond that. We can think of P of d1, d2, dn as some arbitrary polynomial in derivatives. Okay? So in other words, this can be, it needn't even be a polynomial. It could be a power series in derivatives. So this thing can be a sum a m1, m2, mn partial 1 m1 partial 2 m2 partial n mn. Okay, where the a's are constant. So that's, I was thinking of it as a polynomial, but it could be an infinite series. And then what we have is the p of d1, d2, dn on f of x1, xn is then this integral dnk over 2 pi n over 2, and this is just p of ik1 ikn times EI k1 x1 plus kn xn x hat k1 kn. In other words, because these derivatives just pull down IKs, anyway, pull down these IKs, this P, let's think of it as a polynomial. There's no point building a little in power series. So we have polynomial and derivatives acting on a function. It's just the same polynomial in I times K1 through IKN on EIK and then F hat. Okay? But that means that if you have a homogeneous, in fact, an inhomogeneous differential equation, P of d1 dn f of x1 xn equals g of x1 xn, then this, of course, is integral dnk over 2 pi n over 2 p of ik1 dot 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 ikn e to the I. Let me just write this as k dot x, okay, because they're n vectors. I'm just going to call it k dot x. F hat of k1 kn is equal to, we'll write G as a Fourier transform, then that's integral dnk over 2 pi n over 2 e to the I k dot x G hat of K1 Kn. So this differential equation, and let me mention, remember, this is a polynomial derivatives, period. There were no x's here, just derivatives with respect to x. That's why we're not solving all, we're not putting the math department out of business here by solving all differential equations as one Fourier transform. These guys are constants. On the other hand, it's a big class of differential equations that we're solving. So the differential equation looks like this, but in Fourier transform language, it looks like this. But that is just the statement that 0 is integral dnk over 2 pi n over 2 p. Let me write this symbolically as a p of I delta. No, it's not p of I delta. It's p of I k. P of I k f hat of k minus g hat of k e to the I k dot x equals 0. But that means that the solution f hat, or the Fourier transform of the solution f hat of k is g hat of k over p of I k. So you get a solution immediately as simple as that, and then the function f, and let me go back to the conventional notation. You can write it in two ways. F of x equals f of x1 through xn is then integral dnk over 2 pi to the n over 2 e to the I, let me write that though as k dot x, g hat of k1 kn over p of I k1 I kn. Okay? All right, so that's a solution of an arbitrary differential equation with constant coefficients and the variables. So that's the power of the Fourier transform. With the integrals go from minus to plus. Now, there's you might say, well, that's great. What about the homogeneous case? The homogeneous case here, that would give you that would just tell you, by the way, let me just refresh. I've been using some lingo here without explaining it. Somebody should have called me on that. This differential equation is said to be inhomogeneous because there's a g here on the right-hand side. Okay? If g was 0, it would be homogeneous. So we're now looking at the homogeneous equation. Suppose we have the homogeneous equation, ID1, P of D1, P2, Dn, f of x1, xn equals 0. This is the homogeneous equation. All right, well, the analogous equation here is P of ik1, ikn, f hat of k1, kn equals 0. Okay, now you might say, gee, that's pretty confusing. Doesn't that just mean f hat is 0? No. In fact, what it means is that f hat of k1, k2, kn is equal to delta function of, I'm following the notes here, P of ik1, ikn times, and I don't know, I need a better notation here. Maybe I should call this F tilde of K1, Kn minus 1. In other words, one fewer variable. Because this delta function is non-zero only when the variables K1 through Kn are such that the polynomial vanishes. Okay? And when the polynomial vanishes, then that's one equation. P of ik1 ikn equals 0 is one equation which you can use to eliminate k sub n. And then you express kn in terms of k1 through kn minus 1. And that's your expression. So then the solution to the homogeneous equation then is this integral, where now instead, so in the homogeneous case, I use a somewhat briefer notation, dnk over 2 pi n over 2 dvi k dot x, where this is an n-dimensional dot product. F hat then is delta of p of ik1 ikn times f tilde of k1 kn minus 1. Now, in general, you can have you often have more than one solution of the homogeneous equation. And in fact, you probably have many solutions of the homogeneous equation. And so they would appear like this. But then, let's consider the inhomogeneous equation again. If you have a solution to the inhomogeneous equation, then fine. But you can add to it. Let me go over here. Suppose we have P of delta F of x equals P of x. So this is the inhomogeneous equation. All right. Suppose we have the solution of this, which we can call, say F1. So we have P of delta F1 equals G. All right. Now, suppose we also have other solutions that are solutions of the homogeneous equation. Then we can write F of x equal to f1 of x plus f0 of x. And in fact, we can have any number of solutions of the homogeneous equation we can add in together with one solution of the inhomogeneous equation, and that'll give us a more general solution of the inhomogeneous equation. And in the simplest case, the rule is that the general solution of the inhomogeneous equation is a particular solution of the inhomogeneous equation plus the general solution of the homogeneous equation, which I think in fact is true of the general case, because at least for linear equations, linear differential equations. All right, I'm going to give an example now of this technique, but part of this that I think may be confusing us is the use of the delta function. And I'll try to give an example of this right now. I don't know if we'll get through it, but we do have almost 15 minutes, so let's try it. the physics involved is from continuum, the physics of condensed matter, or biophysics. I should say, and biophysics. So let's imagine that we have a certain particles moving, let us say for the moment, randomly. Okay? They could be molecules in a fluid, molecules in a gas, phonons in a solid, maybe. Anyway, things moving randomly. The current density, J, of x and t is minus the diffusion constant times the gradient of the density of these particles. This is called Fick's law. And it's important in biophysics and makes thermodynamics. This D is called the diffusion constant. Diffusion constant. So in other words, what does this mean? This means that if you have in a fluid a region of very high density of these particles, well, let's make it really simple. Suppose you have a region here where you have a very high density over here and none of them over here. Salty water, fresh water. Then you remove the partition and the things diffuse randomly. Well, then the current of salt is going to go this way, the opposite direction of the direction of the density. The gradient of the density goes this way, because it's dense here in sodium, not dense here, but the ions themselves go the opposite way. That's Fick's law. The particles, of course, are conserved here, and so the 4 vector, J, which is equal to rho J, so this is a 4 vector, obeys a conservation law, d by dt, of the integral of rho of x and t, d cubed x, around a certain volume, V, say, is equal to minus the integral of d. Wait a minute now. D by. No, I wasn't looking at my notes. This is clearly equal to minus J of x and t dot dA integrated over the surface of V, or as the mathematicians like to say, the boundary of V. This is white coat notation for boundary of V. And then by, I guess it's Gauss's law, this is minus the integral of del dot J cubed x, again, over V. Okay. On the other hand, this is equal to the integral of rho dot d cubed x, but rho dot, rho dot. Oh, J here. What is J? J is minus d grad rho. So this is equal to minus d integral grad rho d cubed x. And so what we have then is that rho dot is equal to minus d grad rho. Hold it. No, I left out another grad here. This is the divergence of J, and J has another grad in it, grad rho d cubed x. So this is rho dot is equal to minus d grad squared rho. This is called the diffusion equation. And you notice this diffusion equation is an example of the kind of equation we're talking about. Namely, it's an equation that is linear, first of all, in rho. Secondly, it's homogeneous, because there aren't any terms that aren't linear in rho. And thirdly, it involves polynomial and derivatives. And in fact, Fourier invented his transform in order to solve just this equation, and perhaps others. At least that's what Floyd Lauer told me. All right, so how are we going to solve this? Well, we're going to use the technique we just learned. We're going to let rho of x and t be some Fourier transform e to the I k dot x minus omega t rho hat of k and omega dqk t omega. That's a four-dimensional Fourier transform.
Why is it positive ikx and then negative I omega t?
That's arbitrary. In fact, the signs that we use on the exponents are arbitrary. There are two conventions. One is that the Fourier transform is e to the ikx, the other one is that it's minus ikx. But whatever the one is, the inverse has to go the opposite way.
So you're saying in space, for your space,
Yeah.
it's
So
possible.
in other words, over here, all right, can you swing the camera around? So over here, when we do a multidimensional Fourier transform, f of x is actually an inverse Fourier transform. But anyway, f of x equals all of this stuff. The sign of any of these kx terms is arbitrary. But the inverse, in other words, whatever we choose here, we have to have the opposite sign there. Now, the simplest way to do it is have them all pluses here and all minuses there. Or all minuses here and all pluses there. But there was this guy, Einstein, back 100 years ago. He pointed out that the invariant quantity under Lorentz transformations is momentum dotted into position minus energy times time, with a minus sign. And so in field theory, you almost always make this choice in order to have a quantity that's invariant in that exponent. Okay. And now in this case, we're talking about diffusion of particles, and I could have used the plus sign because relativity isn't going to be playing a role in the diffusion of, say, sodium chloride in a glass of water. All right, what's our equation? Our equation is 0. Well, first let's define p. The polynomial p here of grad and d by dt is just d grad squared minus d by dt. And the differential equation is p of grad d by dt on rho equals 0. Right, it's plus. Wow, mistake there. It'll work out. Let's just make sure we have all of these signs right. We started out with d by dt of rho minus the outflow. That's minus the divergence of J. Then J, there's a plus sign here.
So rho dot is.
And so there's a plus sign there. Right? Or do I have it wrong? In that case, there's a minus sign here. And then it's squared. All right? All right, so what is our equation in Fourier transform space? If 0 is equal to integral say d cubed k d omega over, well, I left out the 2 pi's, but that's okay, I'll put it back in. E to the I k dot x minus omega t. And now, the grad, p of grad, what is it? It's d times grad squared. Grad squared is going to bring down a minus k squared. So this is going to be minus d k vector squared. Then minus d by dt is going to bring down a plus I omega. Rho hat of k and omega, all that equals 0. Okay, that's our equation. And so the solution then is that rho hat of k and omega is equal to delta of minus dk squared plus I omega rho tilde of, say, omega. All right? And you may say, gee, I don't quite understand that. Well, hold on a second. Where's some blackboard that I can write on? Maybe I'll try to stand up really tall and write it here. So you get then rho of x and t is equal then, of course, to integral e to the I kx minus omega t rho hat d cubed k d omega, and this is then integral e to the I k dot x. But now what is omega t? Omega is equal to d k squared over I is what this is telling us, right? Suppose if I omega is dk squared, then bingo, that's 0. Okay. So minus I t times omega, right? And omega is d k squared over I. So the i's cancel, and what's left then is a rho tilde of k, d cubed k. And so in fact, this is integral e to the I k dot x minus d k squared t rho tilde of x d cubed k. All right? Now, to figure out what rho tilde is, we set t equal to 0 in this equation. And that tells us that apart from some multiple of 2 pi, rho tilde is just a Fourier transform of the initial distribution at time 0 of the particles, say sodium ions in a glass of water. Okay? So you find that, and then you put that in here, and you get rho of x and t.
It's rho tilde k, right?
Very good, thank you. All right. Well, I think what we'll do is stop at this point. We'll go back to this example next time. You may want to puzzle over this. Yeah. All right, we want to take my office now, and I can print it out and I'll sign it and get it over.
That's painful. Let's see, next homework.
All right. It's going to be do all the problems at the end of first chapter 2 and then chapter 3. I added one, and I'm going to add a second Fourier series problem, and then do all the Fourier transforms. You haven't what?
No.
You haven't? They haven't received them back. Oh, you might not have been in class the day that I. Or why don't you come to my office now along with him? And anybody else have a question? Turn this off.
You know, since the therapy session time has changed,
Wait. Hold